So once the state diagram or even the ASM chart for a finite state machine is derived, writing its HDL to implement it in hardware is mostly mechanical. So what I want to do in this video is to introduce you to this mechanical process. But before I do, I want to introduce a new concept, and that new concept is actually enumerating a new data type. So system Verilog have something very similar to C, which is basically typedef. This command typedef actually defines a new data type. And what I'm defining this new data type, and I'm calling it state type. So you can call it whatever you want to do, but this is very common to call it state type, and you're going to see why in a few minutes. But you could have called it anything, and the same rules that apply to variable names apply here. And the state type at this point, this new data type, doesn't tell me anything. And if I use it, I don't even know what type of data I can take. But for example, if I actually wrote int or something like that in here, I'm basically just renaming the integer into state type. However, this is not very meaningful. So what we're going to be doing is we're going to be defining a new data type and we're going to enumerate it. So what we're going to be doing right now is we're going to enumerate that new data type. And my ultimate goal is I'm creating a new data type that carries out or that contains the state names. Okay, so the state S0, state S1, state S2, and that's basically what we're doing. So this particular command defines a new data type. It's called state type, and the values it can take are the enumeration. This is what enum stands for. So S0 or S1 or S2. So if you define some sort of a signal of state type, it will take one of these values, S0, S1, or S2. Okay, so let's try to see how would defining a new data type or a new signal based on this data type look like. So in here, I basically defined it, and now I started using it. Similar to saying int I or int j, I'm saying, okay, I have a state type data type, and I need a couple of variables. One is called state reg, and the other one is state underscore next. And that's basically what I want to do. So I defined two variables of this particular data type, and these two variables can take the value S0, S1, and S2. Okay. So that's very neat. So now what I'm doing is I renamed my states now, so I don't have to bother. So when you implemented data types before, or when you implemented states by hand, you actually had to code these. This is what we called it state encoding. Okay, and you had to code it, and you have to tell me, well, S0 is maybe 0, 0, or S0 is 0, 1, and 1, 0. And this is why we usually call binary encoding. Basically, you can use a couple of flip-flops to basically two flip-flops to encode these four or these three. This is, I have 1, 2, and 3 in here. So basically, there's one state that is not used, and that's totally fine. Okay, and if you wanted to do it this way by hand for some reason or another, this is the command to do it. So what I'm doing is I'm defining a new data type and I'm enumerating it, and it's actually taking a logic, and it's a couple of bits, and you can basically say that, well, if I say S0, that means I'm doing 0, 0. If I say S1, that means I want basically 0, 1, and if I say S2, that means I need 1, 0. And if for some reason or another you ended up with 1, 1 is not it's not part of that state type. And also, when you studied finite state machines, you have seen that there's another type of encoding that is called a one-hot encoding. So basically, you use 3 bits instead of 1, and you just activate one of the flip-flops per state. And the distinction between both of them, if you guys remember, is that this one here, I'm going to be using a little bit more flip-flops in here. So for 3 states, I'm using 3 flip-flops, a flip-flop per state. It will reduce the complexity of my digital, my combinational part a little bit. And however, it's basically I'm reducing the complexity of the combinational on the cost that I will be using a little bit more storage, as opposed to here, my combination will be a little bit more complicated, but my storage is just restricted to 2 flip-flops. And these basically the two types, basically a binary encoding or one-hot encoding. But as it turns out to be that if you use this particular one in System Verilog, Vivado will actually, by default, generally speaking, it will go to the binary encoding. However, Vivado has some sort of an optimization algorithm internally that it will know which one to implement and which one is better. Should I do binary encoding? Should I do one-hot encoding? So you don't have to specify. So from now on, you're going to see me just using this particular command. I'll just say, here's my new data type, and here are the state names. You go figure out what type of encoding you need to do. And again, the encoding is necessary if you're implementing it in hardware, but we're not instructing Vivado to implement it by hardware. We're describing its behavioral. So the code I'm about to show, or the way I'm about to show you how to code FSM is actually behavioral description of that finite state machine. So this way you don't have to go all the way through implementing the logic by hand and then implementing it and writing code. So I'll review the coding style, and these coding guidelines that we have seen is we need to use always FF with num blocking for register, always com, m blocking for combinational, and you only assign the variable once in one always statement. But what's more relevant to the FSM is actually you need to separate the memory component into individual code segments. What this means is the following, that for finite state machines, I might have different coding styles, and they're all correct. However, one might be a little bit easier, one more verbose and whatnot. So we're going to see today we can have it as a multi-segment coding style, which means that you're going to open a module, you're going to code the state register alone, you're going to code the combinational logic for the next state alone. If you have a mealy and more, you're going to code the mealy alone and the more outputs alone. And this is what we call a multi-segment coding style. Another coding style is actually a two-segment coding style, which tells me, hey, store the state register, basically the sequential in one part, and the combinational inputs, outputs, mealy, whatever it is in just one part. So you have a couple of parts and that's it. And of course you can combine all of them in one segment, but this style I'm not going to cover because it's not intuitive for people that are beginner in Verilog. But the more experience you get with Verilog, you should be able to actually combine it, especially if it's a very simple FSM. But if it's a complicated FSM, what I would recommend is go to the multi-segment coding style. You're going to see this is the most verbose one, but it's the easier to edit and the easier to read, because you can, like if you're changing the mealy output, you can go to that section and just change that and nothing else changed.